Hey guys, welcome back. We're going to look at 20C, which is the derivative function. What the derivative function is, it's a function that you derive from the equation of a either quadratic or any curve. And what it allows us to do is find slope at any given x value. So what does that mean? Well, if I have this quadratic over here, you can see this U shape here. I noticed that at different spots along the graph, there's different slopes. This looks like it could be something like -4, because it's a negative, it's falling from left to right. As we continue along, if I choose another spot right here, the slope is not as steep, might have a slope of something like -1. As I continue along to the right, we see that on the other side, if we have a tangent line here, I see that the slope's increasing, might be something like +1. And finally, as I choose another point, you see that the line gets more steep. As we move to the right, might have a slope of 4 or something like that. So for this quadratic, slope is changing everywhere. So how do I come up with slope of a line that's of a curve that's changing always? Well, we're going to come up with an equation for that, and that's called the derivative function. So basically what it says is, for a nonlinear function, the slope or gradient of tangent changes as we move along the graph. So we saw that. It would change from negative to positive. Then it says we can then therefore describe the gradient function or slope function which, for any given value of x, gives the gradient of the tangent at that point. So the slope at that point. We call this a gradient function or the derived function or the derivative function. So the notation that we're going to use for this new formula and this new function that we come up with is, if our equation is written in terms of y, so say y is equal to whatever, we say dy by dx, and that's the notation for it there. If our function is written as f of x, what we do is we write f dashed x, which has a little slash to it. It's not an exponent, it's just a little slash to our graph. So what does that mean? Basically, if you remember in the last section, what we did was we had functions and we said, well, let's draw a tangent line on here on our own, and then we chose 2 points along the graph and we used our slope formula for it. And we saw that on the same curve, different spots that we choose are more steep or less steep. Then we have a slope of 0, then it becomes more positive and even more positive. So slope's always changing. I can choose 2 spots, that's fine, but what if we don't have a graph? It's a little bit more difficult. So what we do is, anytime we have a function, we'll say ax to the power of n. So an example of something like that might be 2x to the power of 4, or 4x to the power of 3, something like that. Any function where a is going to be the coefficient that we have out front, and n is the exponent. If we want to find the derived function, f dashed x, what we do is we take this n value and we multiply it by the number that's out front. Now it might sound funny, but we take the exponent, we multiply it by the coefficient, so it becomes an. That's our new coefficient. So if the exponent was 4 and the coefficient was 3, well, 4 times 3, that's our new number that we're going to have out front. X is going to stay as x for our variable, and the exponent, what's going to happen up here is we're going to lose 1. So if it was 3, it became 2. If it was 10, it became 9. So if we look at some examples of things like that, like let's suppose I have some function f of x is equal to 3x squared. Well, what am I going to do in this case? Well, I'm going to look at the exponent. I see 2. Coefficient, I see 3, and I'm going to multiply those ones together. 2 times 3, I'm going to get 6. Then I'm going to keep x, and then what we're going to do is we're going to subtract one of our exponents that we have. So our exponent in this case happens to be 2. I'm going to remove 1. 2 take away 1 is just 1. So I don't even need that notation there, but it's just 6x. Now what 6x is the derivative of 3x squared. And what that is the slope formula. So we know that 3x squared looks like a quadratic, maybe something like this. So we have this graph over here. If I want to know the slope at any given spot on my graph, so I want to know the slope right here, where x is equal to, I don't know, 2 for example. What I would do is I would take 2 and I'd put it into the derivative formula. So 6 times 2 will be 12. The slope of that line, of the tangent to that line, I'll pick blue for example. The slope that we would have here would be 12. So let's try another number on this graph. Let's suppose I wanted to find out the slope. Let's suppose I want to find the slope on the left side. So let's suppose we have a value of something like -2. The dot would be right here. I want to find the slope of that. So if I look at this one, you might see that, well, that slope's going to be negative. Because I can tell that it's decreasing like this. Just a rough graph for it. But I want to know what is it. So I'm going to take -2 and I'm going to put it into this formula for x. And I have 6 times -2. Well, the slope of that blue line there would be -12. Right? It's decreasing. So let's look at some examples down below. If we were looking for the gradient function or slope function or the derivative, well, of these ones, I'm going to take that 8 and multiply by the number out front. Well, there is no number there, so you can imagine it to be 1. So it's going to be 8 times 1, which is 8, and that's where we get the 8 from. And I subtract 1 from the exponent, and that's where we get that 7 from. We get 8x to the power of 7. So if we graph this thing, 8x, or x to the power of 8, looks something like this. I can choose any value of x and substitute it in to find out the slope anywhere along that graph. One thing that's a little bit different is that we have this one over here where we have 3 on the bottom, and you might remember from grade 11 or even grade 10, maybe the end of grade 9 even, when we have an exponent on the bottom, that just means that it has a negative exponent if we were to write it on its own. So those are the same. 1 over x to the power of 3 is the same thing as x to the power of -3. Now you're going to want to write it like this when we find our derivative because it's going to be a lot easier than working with those fractions. We'll look at those ones in another section, but for now, if we have 1 over x to the power of something, just write it as x to the power of negative that. Reason being, it's a lot easier to find the derivative because I take -3 and multiply by the number out front. -3 times 1, which is -3. That's where we get the front from. X stays as x, and then we lose one of the exponents. So it was -3, and I take one away. That's where we get this -4. And there we go. For the next one, this one has us actually looking at an equation and finding out the slope for it. So this one says, consider the function f of x is equal to 1 over x squared. We know from the example that we just looked at, we can write that as f of x is equal to x to the power of -2. And that's fine. They're the same thing. It's going to be a lot easier to find out our derivative in that form because we know that we can take that -2 and multiply it by the number out front, which in this case is 1. Subtract 1 from our exponent, and we would end up with our derivative here. Or I can write that as a fraction by just taking that x to the power of -3 and putting it now back down on the bottom once I've used it. Either of them are fine. You can use one or the other. But part 2 says, I want to know what the slope is. Find and interpret f dashed 1. So that's saying, well, here's our function here graphed. Right, our function looks this. Here's our function, that black line we have there. And we have a dot here where x is equal to 1. And I want to know what's the slope of that tangent line. Well, that red line is the tangent line. It looks negative to me. But what do? Well, if we have x is equal to 1 and I want to find out the slope of that, I'm going to take 1 and we're going to input that 1 right into our equation for x. Or you can put it into the other one as well for x, but doesn't matter. Regardless, it's been done on your page and you can see that it becomes, I'll zoom out here, it becomes -2 when I input 1 in for x. So that means the slope of that red line over there on the right is -2. It's falling to the right. Makes sense. And there we go. All right, so in terms of the homework questions, we had these down here. Basically what they wanted you to do was find those derivative formulas, or gradient formula we can call it. So essentially what we're going to do is we're going to always take that exponent that's out front, multiply it by the coefficient, and then reduce the exponent by 1. So for the first one, if I was looking for the gradient, dy over dx, well, 6 comes out front, so it's going to be 6x, and I'm going to lose one of the exponents. It's going to become 6x to the power of 5. So if I wanted the slope of any x value along the graph of y is equal to x to the power of 6, I would input that value of x into that derivative formula. Second one that we have over here, same idea. I know that this is equal to y is equal to x to the power of negative 5. So if I'm looking for the derivative of that, dy of dx, I'll take that negative 5, it'll come out front. X stays the same, and I lose one of my exponents, becomes negative 6. Next one, y is equal to x to the power of 9, same idea, dy over dx. 9 is going to become the new coefficient out front because 9 times 1 is 9. X stays the same, and we lose one of our exponents. And same goes for the last one. We have x to the power of 7. I know that's the same as y is equal to x to the power of negative 7. So if I'm looking for my derivative, dy over dx, it's going to become negative 7x to the negative 8 because we lose one of our exponents. Continuing through, next one says, for f of x is equal to x is equal to 5, find f of 2. That just means input 2 into the equation. 2 to the power of 5. That means 2 times 2 times 2 times 2 times 2, and 2 to the power of 5 is 32. All right, next we have f dashed 2. So I'd have to find out what f dashed is. F dashed of x, well, that's the derivative of that, which is 5x to the power of 4. So that's the slope formula. And if I want to know, well, what is the slope of that function at x is equal to 2, I would input 2 into that equation. And I put 2 to the power of 4, which is 16, multiply that by 5, and we get 80. So it'd be very steep at that part of the graph. And you get the idea, kind of the same idea for the other two that we have. We're just going to put a negative 1 or negative 1 into the derivative formula. So you get the idea for those two. Next one, as we work through, it says, consider f of x is equal to x to the power of negative 4. So we can consider it. Great, I've considered it. Now it says, find f dashed x. So that means find the derivative of that. Well, one way that we can work with that is, let's simplify it. I know that that's x to the power of negative 4. Right, because when it's on the bottom. Now if I'm looking for f prime x, well, I know that that negative 4 is going to come out, or f dashed x. Negative 4 is going to come out. We're going to have x to the negative 5. So that's our gradient formula, or our derived formula. If I'm trying to find out f dashed 1 or f prime 1, well, I'm going to put 1 into that. So it's going to be negative 4 times 1 to the power of negative 5, which is just negative 4. That means the slope of that spot is going to be negative 4. And that's those ones. So you just kind of get the idea. They're kind of repetitive here. And as we look at the last one here, this one says the graph of this is shown over here on the right. So that's x cubed over there on the right. Its tangent at negative 1 and negative 1 is on our graph. So I see that one over there on the right. That's the red graph. It says use the graph of the gradient of the tangent. Or use the graph to find the gradient of the tangent. So we choose two spots on the graph. So let's suppose I choose here at 0 and 2. And I can choose the point at negative 1 and 1. I don't have to write it, it's already there. And I can use the slope formula of that. So I know y2 minus y1, 2 minus negative 1, all over x2 minus x1, 0 minus negative 1, will work out to be 3 over 1, which is 3. So I know the slope of that red line is 3. Then it says use your derivative in order to find that out as well and see if it's also negative 3. So let's test it and see. So it should be if we've done everything properly. So I'm going to find out what f dash or f prime of negative 1 is, or of x is. Well, I know that my function is f of x is equal to x to the power of 3. Exponent comes out and I lose one of the exponents. Then from there, I want to find out what is my slope when x is equal to negative 1. So I'm going to input negative 1 into this formula. Well, negative 1 squared is 1 times 3 is 3. So I get the same value both ways. It does not matter which way we take. If we don't have a graph, well, we'll use those derivatives to help us find out the slope. But if you have the graph all on there, you could use the graph in order to find it. Usually it's best to use the formula because if you're drawing your own tangent line on, yours might be a little bit more steep than somebody else's, whereas the formula for the gradient formula or the derivative is always going to be more precise.